In this short video, we'll look at Bode diagrams. Bode diagrams are essentially frequency responses of linear time invariant transfer functions. Now let's look at some preliminaries. Given a transfer function g of s, which is output by input, y of s is the Laplace transform of the output, u of s is the Laplace transform of the input, and given an input signal which is a pure sinusoid, I claim that the output is given by y of t is m times sine omega t plus phi g, where m is the magnitude of the transfer function evaluated at j omega, and phi g is the angle of the transfer function evaluated at j omega. Omega is the frequency of the input signal in radians per second. Consider a transfer function g of s, which is y of s divided by u of s, is given by this expression. Here z1, z2 up to zm are the zeros of the transfer function, p1, p2 up to pn are the poles of the transfer function. The question is, what is the output y of t when input is a pure sinusoid? So u of t is sine omega t. So if you take the Laplace of the input, or Laplace of sine omega t, you know that you get u of s is omega divided by s squared plus omega squared. You substitute in this equation to get an expression for y of s as g of s times u of s. This here is g of s, and this is u of s. Now let's look at the partial fraction expansion of y of s. So that is y of s. You can write this as this with partial fraction expansion. We've covered this before in partial fraction expansions. Now these two terms here are because of this term, which is the input. Now the right hand side is also equal to g of s times omega divided by s squared plus omega squared. Now what we'll do is we'll multiply both sides by s squared plus omega squared and set s equal to j omega. Let's do that. And if you do that, these denominators get cancelled by this, and this denominator gets cancelled by this. What you're left with is s squared plus omega squared times all these terms plus alpha plus beta j omega, that is equal to g evaluated at j omega times omega. Set s equal to j omega, s squared becomes minus omega squared, this whole thing drops out, and therefore you can write alpha plus j beta omega, as the left hand side, is equal to g, the transfer function evaluated at j omega times omega. So this is a complex number, and if I represent it graphically like that, this is the imaginary part right here, this is the real part right here, and this is the angle. So this complex number has both angle and magnitude. Let's look at the angle. The angle is given by tan inverse of beta omega divided by alpha. So this angle is tan inverse of this distance, which is beta omega, divided by this distance, which is alpha. On the right hand side, if you take the angle of g evaluated j omega times omega, that can be written as angle of g evaluated at j omega plus angle of omega. Omega is a real number, therefore that angle becomes evaluates to 0. So I can write angle of g evaluated at j omega is phi g, which is equal to tan inverse of beta omega divided by alpha. This is the phase of the transfer function. Now if you do the magnitude of this expression on both sides, magnitude of this complex number is root of alpha squared plus beta omega the whole squared. This is equal to the magnitude of the transfer function evaluated at j omega times omega. Now let's go back to y of s and invert the Laplace transform to get y of t. If we do that, we get this expression where a1, a2, a3 are constants that you find. Now these two special terms end up in this expression here. So alpha divided by s squared plus omega squared, Laplace inverse of that is alpha divided by omega sine omega t, and this expression here ends up being beta cos omega t. Now Assuming a stable transfer function, what that means is all the poles are in the left half plane. So P1, P2, P3 up to Pn greater than 0. And if you look at the steady state response, the steady state response is when t is very large. All these terms end up being 0 because this exponent terms ends up being 0. So we get the steady state response YSS as alpha divided by omega times sine omega t plus beta times cos omega t. Writing m dash as root of alpha divided by omega the whole squared plus beta squared, we can rewrite YSS as this expression here. Essentially what I'm doing is multiplying and dividing this expression by m dash. Now we'll call this term cos phi and this term sin phi. You can check this is valid, because if you do cos squared plus sin squared, you'll get equal to 1. And using the identity cos phi times sin omega t plus sin phi times cos omega t is equal to sin omega t plus phi, we can write YSS as m dash, which is this, times sin omega t plus phi. Now we can write a tan phi, which is sin phi divided by cos phi, from here as this term divided by this term, and that ends up giving me phi is tan inverse of beta omega divided by alpha. And if you recall, this is the same as the phase contributed by the transfer function. And if I take the expression m dash, which is this, I can reduce it to this form. All I've done is cross multiplied by omega squared here and brought omega out of the square root sign. Now this, if you recall, is nothing but the amplitude of the transfer function evaluated at omega, and therefore I can write y steady state is magnitude of g evaluated at j omega times sine omega t plus phi g, which is what I initially set out to prove. So what this essentially says, a linear time invariant transfer function does not change the input frequency. All it does is it magnifies or attenuates the amplitude and adds a phase. So what does this actually mean? So if you have a transfer function, linear time invariant transfer function like this, a system like this, you give an input u of t and an output y of t. This is how it's going to look if the input is a pure sinusoid. Here the blue is the input, which is a pure sinusoid. The output is the red, which is again a pure sinusoid with the same frequency, but it lags the input by tau, and tau is related to the phase contributed by the transfer function phi g as tau omega equal to phi g, and amplitude undergoes some magnification, and the magnification is given by the magnitude of the transfer function evaluated at j omega.